Okay, this is 3.4a, College Algebra, Theorems about Zeros of Polynomial Functions on page 290. So this is going to take several videos, which is fine. Make sure that I have a chance to explain everything that we're doing. What we're going to do in this section is now we're going to look at polynomial functions that have complex numbers as their coefficients. So instead of something like 5x cubed minus 3x squared plus 2, which is a polynomial function, we're going to allow things like 5x cubed minus 3x squared plus 2 plus 4i x plus I. So we're going to start allowing things like that. So anyway, the fundamental theorem of algebra. One of the things that you really never teach in lower algebra that I'm going to throw out there for you right now is that when we have a linear polynomial function, it can be always written in this form, y equals mx plus b, where the zero of the equation, or the root, or the answer, there's only one place that a line will cross the x-axis, and it will always cross the x-axis at the opposite, the y-intercept, over the slope. So negative b over m, that will always be where the line crosses the x-intercept, or the x-axis. And it will only cross at one place. Now, when we're talking about quadratics, when we have like an x squared, we will have at most two answers, two places that it crosses the graph, like right there. Or it could cross it at just one. It could just be tangent like that. So those are your two answers. Now again, you're going to get two x's. You'll just get two x's that are the same number there because you're dealing with a quadratic. Okay. The fundamental theorem of algebra says on the bottom of page 290, every polynomial function that has a degree of n, so it has an exponent, and that exponent is greater 1, it will have at least one zero in the system of complex numbers. So you're going to have at least one place that this we have a zero in the set of complex numbers. So notice, I didn't say a place where it will cross the x-axis because we're talking complex numbers now, and that doesn't necessarily mean it will cross the x-axis. All right, bottom of the page, 290. The zeros of a polynomial function are the solutions of the polynomial equation where you make y or f of x equal to 0. So zeros of a polynomial function. And again, I've mentioned this before, a function is going to be written like that. And when I'm talking about a polynomial equation, we're going to substitute 0 for f of x so that we can find out where where we have the graph crosses the x-axis. So, every polynomial function of degree n with n greater than or equal to 1 can be factored into n linear functions, not necessarily unique. All right, that's bottom of page 290. And what that says is that every polynomial function, so let me give you a polynomial function here, x cubed minus x squared plus 9x minus 9. Okay, so there's a polynomial function. In fact, I'll say that that equals f of x just to make sure you realize that that's a function. Every polynomial function, it says, bottom of page 290, with a degree n. So here's my degree. So n just represents whatever number that is. When n is greater than or equal to 1, can be factored into this many linear factors. So again, we've talked about it can be factored in and have that many answers. But it does say not necessarily unique, which means we could have x equal to 3, 3, and 2. So 3 answers, but they don't have to be unique answers. Some of those answers can be the same number, and that's okay. So that's what it's saying. In fact, it says it can be factored into some kind of a coefficient, or just number, and then another number we'll call C, and another number we'll call C2, and another number we'll call C3. So what that's saying is that this polynomial function is going to give me 3 answers. 1, 2, 3, and then some kind of coefficient here. But just to make it easier, we're going to make it so that coefficient is 1 at this point. So anyway, top of page 291, let's practice one of these, okay? So let's go ahead and use that same equation I just had up there, but we're going to go a little bit different. It says here in example 1, find a polynomial function of degree 3 having the zeros 1, 3i, and negative 3i. So it needs to have as its zeros 1, 3i, and negative 3i. Okay, now before I said at the bottom of page 290 that they're always going to be written like this, and all that C1, C2, and C3 is 3, is the factors. So what we're going to do is we're going to take and say, okay, so if this number is this, then we've got x minus 1. If this number is this, we have x minus 3i. And if this number is this, we have x plus 3i. Because notice what we've got is we came up with a factor, whereas when we put this in for x, it gives a 0. When we put this in for x, it gives a 0. And we put this in for x, it gives a 0. So we're looking for factors that when we put our roots in, we're going to get 0. So that will equal 0. And there's some coefficient in front of my factors here, and we're just going to make it a 1. So understand here that the reason this can be any number at all is because whenever one of these factors is 0, when we take 0 times this, times this, times this number here, everything becomes a 0. So it doesn't really matter what this number is, but we're just going to make it a 1 because it's the simplest polynomial that we can come up with. All right, so now if we were to take these three binomials and we were to multiply them, we would end up with x cubed minus x squared plus 9x minus 9. And that's what it asked me to do. Find a polynomial function, so I'm going to end it with an f of x because then it becomes a function that has these for its answers. So I just went backwards. I put these into 3 binomial factors, and then I did the FOIL method, and I ended up with that I have squared out in red there. Okay, so let's look at example 2. And this is where we're going to use some multiplicity stuff. Find a polynomial function that has a degree of 5. So my degree is going to be 5. And negative 1 as a 0 with a multiplicity of 3. 4 as a 0 with a multiplicity of 1. And 0 as a 0 with a multiplicity of 1. Okay, so here we go. We're going to let our an, our coefficient in front of our factors, be 1 again. So what we get is we get f of x equals, and let's look at the negative 1, x plus 1 with a multiplicity of 3. X minus 4 with a multiplicity of 1. And x minus 0 with a multiplicity of 1. Okay, so then we're going to just use the FOIL method. Kind of the FOIL method, I guess, but you're just multiplying everything, and you end up with x to the 5th minus x to the 4th minus 9x cubed minus 11x squared minus 4x. And notice we have a degree of 5, and we just did FOIL. So I'm not showing you how to do that because I'm assuming since Algebra 1 you've been doing this, and you should be fine. So that's the first couple pages, and we'll continue on with 3.4b.